Okay, so hi everyone. Thanks for joining me for this talk about building recommendation systems at scale. So a little bit about me. So I'm Omri. I'm a data architect at Natural Intelligence. And for the last 3 or 4 years, I'm building recommendation systems, and I'm getting obsessed about building data-driven experiences. And my other obsession is Lego, but we'll get to that later. So why are we talking about recommendation systems? Recommendation systems eventually are everywhere. They're on your favorite shopping website. That's my favorite shopping website, mostly because I built it. They're on Netflix when you open TV. They're on McDonald's when you're looking for lunch. And they're even on the street. I took that photo 2 days ago at Malmo's city center. And this ad from Audible is promising that they have the largest selection of audiobooks for the kind of people who Google stuff like "Do Dead Souls Know Morse Code?" Oddly specific. So I've actually typed it down on Google, and I found it's directing to Stephen Fry's new book, which is, again, oddly specific. So I've looked on Google search traffic, and it seems that in Scandinavian nations, Stephen Fry is almost as popular as just after the UK and Ireland, even before Australia, New Zealand, Canada. So, yay, I think they're doing something smart. So today, specifically, I want to talk with you about how to implement recommendation system at scale with ElasticSearch. Now, the first question that might pop into your mind is, why do we do such a thing? And to get in order to answer that, we'll need to get into the definition of what is a recommendation system. So let's think about the definition for a minute. A definition that I like is something like, give me the most relevant content in relevance to the user, who am I, and the context, what context am I at right now. Now let's look at the definition for search engine. What is a search engine? Give me the most relevant content in relevance to some free text query I'm typing. And actually, that became, in the last 20, 30 years, a little bit of a lie, because it's more like, give me the most relevant content in relevance to a free text query, who am I, and the context I'm in. And you want a proof for that? Here's the proof. So here's me Googling for the term football in Israel. And not surprisingly, I will find results like the Premier League and the definition of football as we know it. Now, this is my American cousin typing the same search term, football, in the US. And you'll find another kind of game, which I really don't think can be called football, but Americans. So yeah, Google doesn't only look on what I search, but also who am I and where I come from. And this ability to use search technology to create recommendation engines is what I call search commendations. And why should we use search for recommendation? Why should we use search commendations? And the point I will make in the next few slides is that search commendations, or using search for recommendations, is actually a great idea. Why? First, because it solves a really, really basic problem that we have today, which is creating recommendation at scale. Recommendation at scale is hard. Search and scale, on the other hand, is a solved problem. Google are doing it. Almost everyone can do it. So if we can use the same technology we use for search and we know how to use it at scale, we can create better recommendation system. The second argument is that ranking, which is a basic part of building recommendation engines, building and tuning recommendation engines, is a first-class citizen on search engines. And we can leverage that to create recommendation engines really, really in an easy manner. The third argument is that we know how to create search engines that will give us answers in real time. For recommendation engines, it's still a little bit harder. And the fourth argument is that developers, eventually, we understand search. Recommendations, a little bit less. So in this demo, in the slides, I'm actually going to show you a demo of how to build your own recommendation engine using ElasticSearch. Now, ElasticSearch can do a lot of things beyond search. It can do collaborative filtering, which we will talk later today. It can do anomaly detection. It can do more like this analysis, so you can actually give it a document or give it an item and to do some analysis and say, okay, these are all the items that are similar to it. It can do trend analysis, but we're not going to talk about any of this. Today we're going to focus on something called content-based recommender systems. So what is a content-based recommender systems? It's basically very similar to what you see on Netflix, Apple TV, your Facebook newsfeed. It's basically content, the most relevant content to you. So how do we build content-based recommender systems? We're going to do it in just 3 simple steps. So step 1, we need to model our content. And to model our content, first we need to understand what are the basic building blocks of content-based recommender system. And the basic building blocks are stories and tags. Stories are basically pieces of content. They can be an article, they can be a product, they can be a video on YouTube. All of these can be eligible to be stored, so why don't I call them just item or content? Because stories have some very, very slight distinction, which is very interesting. Stories expire. A recommendation I gave yesterday is probably less relevant than the recommendation I give today. A video from 5 years ago is probably less relevant than a video I can recommend from 2 days ago. Story is basically just a document, a data object. It can contain whatever we need in order to make our recommendation. So basically, it can be the content. It can be any metadata that we might choose to recommend upon the type, when it was created, who wrote it, who created it. It might contain also social indicators, how many likes, shares, comments, clicks, views it might have. And it might contain some quality indicators, for example, quality of the images, number of images, how many click it has, which is a little bit more objective than just shares. The source of the quality, how much we trust the source, and yes, even the timeliness. Tags, on the other hand, are just, in a way, a topical classification. So each story, I can say, yeah, I tag this story as running shoes or shoes. And again, with a slight distinction. Unlike regular tagging, tagging for recommendation systems come with scoring. They can be curated manually, so I can actually create this tag manually based on data that I have, and they can be generated algorithmically, and in about 20 minutes I'll show you how. So we can see here 2 examples for tags that I have on my document. An interesting thing to see is that the scores, in a way, represent hierarchy. So how much we believe this story is relevant to this tag. So for example, for a running shoe, we might give it a high score for being a running shoe and a little less, and a little small score for category of shoes. Why? Because it's much more relevant, much more interesting to know that it's a running shoe than a shoe. So let's take an example for this interesting item that we wish to recommend. So let's see what it might have, what kind of metadata attribute it might have. So it might have the amount of likes, the amount of comments, views, who created it, who wrote it, the type of the content I'm trying to recommend right now, and even when it was created. I can tag it by a lot of other tags, the brand, the category, the color, and again, give some score. Some of the tags don't need to be humanly readable or meaningful, but they are still very, very useful, and we'll get to that later on. So let's take this content that we've built, and let's try to formalize it as an ElasticSearch document. So let's have a small demo and see how it works. So I've created a new ElasticSearch engine. It's sitting on Amazon's cloud, and let's see what we can get from it. And let's do a query, and we can see that our index has some as a mapping definition. A mapping definition basically defines what are the different fields and field types that a story might have. So our story has the actor, the amount of comments, an actual text that represent the content, the CTR, click-through rate, how many people of those who viewed this, this piece of content actually clicked on and converted, the date it was published, liked, story ID, story type, and so on and so on. And eventually it has a list of tags, and each tag has, additionally to the tag ID, it has tag score that we can later use. Now, I have an example here, for example, of a product that I've added to my index. We can see that we have a product, Lego Friends Central Perk, and that's the model number. I've tagged it as Lego, and this is the score. I've tagged it as Friends TV, and this is the score I gave it. It has some likes, views, CTR, and so on and so on. And we can actually fetch it together with all the rest of our documents. And here we can see the list of all the products that I have on my index. So I have the Lego Disneyland train station, and the Lego Friends Central Perk, and Lego Jurassic Park T-Rex, and so on and so on. And each of them has different tags and different score for each tag. But what I do want you to look at right now is this score field. This score field basically says, OK, so I want to return all the documents right now, and I will try to score them. Elasticsearch basically gives wherever you ask it to score something or wherever you don't, it will give a score according to the query you're doing. So currently, all the documents have the same score because I didn't give it any scoring script. But later on, it will be ranked and will be scored according to the scoring script we'll build. So we have our index, and it's full of Lego products, which is really, really nice. So let's get to step 2. Actually, writing our ranking scripts. Now it's the time to get from 200, 300 products, or in our demo case, 8 products, into the top 3 that might be most relevant to me. So how Elasticsearch scoring works. Basically, there are a lot of techniques to use scoring. The technique we're going to use today is something called scripted scoring, mostly because it allows us to really express a complex way or a complex model to score documents. This is how it looks like. That's a very, very simple query. What it say, OK, just return all the documents and score them according to some scripts, and you may enter some parameters externally. So let's start writing our scoring script. So first of all, we want to recommend our best content. And what might indicate for content to be good or best? It might be the content type. We know that videos convert better than text. We know that products or deals convert less than deals, and so on and so on. There might be creators or might be authors that we trust more, that are proven to give more quality content. We might use the CTR, the click-through rate. If we see that a lot of people click on this content, we can give it a nice score. And we might use, or in a way, balance it by clickbaiting a score. So look for all those keywords that might indicate that this item, this piece of content is clickbaity, and choose to, again, promote it or not, according to what our business need is. So how the script might look like? Basically, what we do is we take the values for all of these metadata values, and we multiply them by some weight that we, for now, chose arbitrarily. So that's quite simple. But what about likes, comments, share? We can do the same trick, but that might bring us into a problem. And this problem is what I like to call which will get richer. So let's say I have a story, a piece of content that got few likes, so it started to appear higher and higher. And since it's appearing higher and higher, it might get more likes and more likes and more likes. And now new content doesn't have a chance to even fight this game. Another thing that makes social indicators a little bit more sensitive is what we call bots and vote brigades. Because it's user-generated, it's very, very sensitive for playing with. So a trick we can do is actually use a log rule. What is a log rule? Actually say that the first 10 likes are worth as the next 100 and worth as the next 1,000. So if I have 5 likes, it will be something like 0.69. If I have 50 likes, it's 1.69. If I have 500 likes, it's 2.69. And 5,000 likes, 3.69. As you can see with this log rule, we somewhat mediate the effect of user-generated content or user-generated likes on our content. So this is how it looks in our script. And basically, we have it. We can now recommend, even if naively, our best content, which is not bad, except for one thing. We now recommend our best content ever. And that can be good. But it's not very useful for our recommendation system, because if I'll give you a recommendation system that shows the best movies ever, yeah, you might use it, and you might find a new movie that you haven't seen, but it's probably good for only one time. And we want our content system, our content recommendation to be worth something for the second time and the third time. And for that, we'll introduce a concept called timeliness, or how we can decay our stories, how to make them expire as time moves on. A nice trick to do that is just to set a decay rate and just create an exponential decay. You can create your own decay function as you wish. We found this function to be working very well. Another trick that we're doing is actually creating variant decay functions. So we're playing with our decay factor according to who the user is. So if, for example, you're entering Facebook only once a week, you will see stories which are good, but a little bit older. If you enter Facebook every 15 minutes, you will always see fresh content. So another small thing I want to mention regarding decay, which is a little bit connected to the world of performance. Now, calculating exponents and calculating decay functions on query time might be resource exhaustive. So a small technique that you can use is to actually calculate the decay on index time rather than on query time. So you can actually, instead of calculating this exponent while you query, you can make sure that new stores will get exponentially higher score as they get into the system. So great, we now recommend high quality and fresh content, but we're still missing something. And to show what we're missing, I'll tell you a personal story. So 2 years ago, I went to visit Japan, and I was looking for a hotel in Tokyo. And these are the recommendations I got from Google. And all of them are high quality and fresh and have great reviews and great location. But there's one thing Google missed. Can you guess what it is? This is what they missed. And what they missed is an hotel called Hotel Grocery Shinjuku, also known as the Godzilla Hotel. And with all due respect for all of these high-ranking hotels, I cannot, as a true geek, I cannot miss a night with Godzilla in my room. So, so what Google was missing? Google was missing the fact that I'm a geek. And Google was missing the concept of personalization. So, and to do that, we're gonna introduce a new concept into our system, my interest. My interests, in a way, are very similar to tags. In the basic, these are my interests, and they are just a key value structure of some key, some category or topic, and the score that shows how much I'm interested in them. So I'm interested. So my interest in Lego, for example, is 1.0, and Star Wars 1.5, and so on and so on. So now that I have my interest, first of all, I can query out, I can filter out all the terms that probably are not in my interest collection. So I don't want to see yellow socks. I can just filter them out and make the query a lot more faster. The other thing that I can do is I can actually score my content according to the story tags and my user interest. What I do is a rather simple calculation. I take my user interest, my score for my user interest. I see if a specific story has the same topic in it, and then I multiply it by the topic relevancy. And then I can create a story score for each of the stories, which shows how much this story is relevant to me. How it looks in code, something like that. So all I need to do is just take from the parameters all of my interest, I'll take my tag, and I'll just multiply it by the score of the tag of the story. And all I need to do is just state all the tags that I'm interested in and their relevant score. So now I have a score. So now my score is built from personalization score, quality score, social score, and time decay. So let's see how it works and do it live. So we've seen how all of these stories actually have the same score right now. So I want to show you another query that I've built. This query asks only for the first three items, and it will ask only for items that are in my interest. So the Lego, Christmas, Star Wars, and things that are fancy. And I even told them that Lego is scored 2.0, and Star Wars 5.6, and I really, really like things for Christmas, and yeah, I like fancy things. And let's see how it all works. Now, eventually, I've a little bit simplified the entire scoring, so I've only included the personalization score and the social weight, but again, you can add all the previous part that I've shown you. So let's run it. And OK, so let's see what we've got. So first, we've got our items ordered and ranked according to the score. Now you can see the score that, for example, Lego Winter Train is showing up first, and then Lego Jurassic Park, and Lego Disneyland Train, and so on and so on. Let's try to play a little bit with the score and see what will happen when we do that. So let's say I'm really, really into Star Wars, and I less like fancy things, and let's see what will happen. OK, so now Lego Winter Train is up, and Lego Star Wars Millennium Falcon, again, up, and Lego Star Wars Advent Calendar, again, is up. So when playing with these interest scores, I can actually play and show and create personalized experiences for my users. So step 3. That was a bit simple, right? Too simple to be working well at scale. Well, that's true, because there are missing parts here. There are missing parts that, in a way, I was hiding to make it a little bit simple. So, for example, missing part is how do I choose my weights? How do I choose what factors is weighted how? How do I tag my content? I assume that someone somewhere magical gave me tags and scores for each of my stories. How can I calculate my user interest? How can I measure relevance? How can I prove that my recommendation engine actually works? And what about collaborative filtering, deep learning, and all of these nice machine learning terms? So they're there. Something that you need to remember, that the concept of using recommendation engines is still valid. The point is that you can start small and simple, and then you can add other technology stacks, other techniques to make the recommendations better later on. You measure, and then you optimize accordingly. Something that we learn along the way, that really, really, the simple measures worked just fine for the beginning. It started to get complicated as you get to more and more and more products. For 60 million products, yeah, this simple technique, while still keep working, you need to give it more tag, more and more metrics to make it work better. So let's deep dive to some of the more interesting parts of it. So the first thing is, okay, so you said you need to optimize and measure. So how do we measure? So there's some techniques we're using to measure our recommendation system. One is something called mechanical torque or user testing. Who knows what mechanical torque is? Basically, it's a service that allows you to send your results into people around the world, and for a few cents, they will give you one answer, a human answer, and that's a nice part. So you can send a lot of various or varying recommendation results according to some tweaking you did to the weights or your tagging, and you can ask them, okay, which one is better? This recommendation is this recommendation? And using this feedback, you can actually create a testing set that you can optimize upon. Another thing that we're using is actually using our real users, A/B testing. We're giving 50% of our users this experience and 50% of our users that experience, and see which work better, which leverages CTR, which leverages our metrics. And the most importantly, we're building benchmarks and benchmark data sets, which allowed us to test our recommendation engines under lab conditions. So we don't need always to send it to the users to see if something went wrong or not. But when you measure things, there's something you need to be aware. It's called the accuracy bubble. Usually when you measure things and you measure only one metric, for example, relevancy or CTR, you might get a result like this. So I believe you all got this experience that you're buying a refrigerator at Amazon, and for the next 4 years, you're getting more recommendations for more refrigerators, because that's exactly what you need today. And that's the accuracy bubble. I want to show you another example of it and how you might be able to fix it. So, for example, for users who watched Police Academy, a system that only looks on accuracy might recommend the other Police Academy films. We want to look on other metrics as well to improve our recommendation system. Other metrics that we might use is diversity, novelty or serendipity. The link below shows actually how to calculate these metrics on your data sets and create a more diverse, a more interesting recommendation. So for example, if I've watched Police Academy 2, the second results might show a little bit better or more interesting recommendations, fun and stupid comedies in this case. So another question that you might ask is, how can I create better tags at scale? Because what I've shown you today assumes that you have a tag or can create tags based on your content. And that's not always true, at least not always you can create high quality tags on your content. So how can we do that? There are families of algorithms, collaborative filtering, KNN Matrix Factorization that helps you create, basically create tags from behavior. What it means, so let's say I have a list of movies and users and how many times they've watched this movie. Allegedly, I cannot do much with this data, right? I cannot say this is a comedy or this is an action movie, right? But there are some algorithms that can say something interesting, which is not that bad. For example, there are algorithms such as matrix factorization or collaborative filtering that can say that whoever watched one of these movies are more likely to watch any of the other movies from this list. When you look behind the scenes, the pattern that it found by only using the behavioral data is actually that people who like Will Ferrell movies will like Will Ferrell movies. And the neat part is that it doesn't know who Will Ferrell is and that people who like Will Ferrell movies like Will Ferrell movies. It just knows that people who love one of these movies will like other types of movies. So that's nice. And it gets a little bit more complicated and a little bit more interesting in this example. So whoever likes one of these TV shows, we like other of these TV shows. Now here, the relation is a little bit less obvious. I cannot name it in any way, but it's valid nonetheless. And the technique to do it is a technique called matrix factorization. It contains a lot of equations and linear algebra, but you don't need to be worried about that. There are two nice libraries that can help you use that. They are actually documented really well, and they hide a lot of the mathematics and the complex parts of how to do that. But I do wish to give you a little bit feeling of how it works behind the scenes. So I took a lot of Lego products, and I've asked it to give me two tags or two dimensions that I can work with, and to rank these products according to these two dimensions. So we can see it placed these products on these two dimensions, which is all fun and games, but it did something even more interesting. It put the users on those two dimensions as well. So we can see that this guy, for example, is more likely to buy this speed car and that Beetle van, and let's say that this guy over there is more likely to buy the expensive or the less expensive Millennium Falcon. And what actually happened behind the scene, and again, the machine doesn't know that. It doesn't know that it found this relation. Just knows that this pattern exists. Is that it found a relation between expensive and cheap products, and that there are some people who might prefer, and that people who will prefer cheap products will prefer other cheap products, and those who prefer expensive products will prefer other expensive products. And found another relation that there are people who like cars, usually like cars, and there are people who like spaceships, and they will usually like spaceships. And the neat part is that I can put a user everywhere on this graph. So let's say I put it near the speed car, and now I can recommend for him, if I put this user on the speed car because he bought the speed car, I can easily say, okay, he might be interested also in the Volkswagen Beetle van, or in this space vehicle, something like that, which is, again, a nice trick. The last part I would like to talk with you about is about performance and scale. So if you wish to reach over 1,000 requests per second for your recommendation engine, which contains 1.2 billion stories with latency of less than 100 milliseconds, there are compromises to be made. Again, what I've shown you is relatively naive, but it's scalable. And these compromises are the following, or this is what we've found over the years. So one thing you need to think about is what calculations we do on index time and what we do on query time. The more we will do on query time, we'll have our calculation will be longer, but on the other hand, we'll be able to do more things. For example, play with our weights or play with other factors in the calculation. Another thing that we need to think about is filtering versus ranking. So one thing that we can do is, for example, I have 1.2 billion items to recommend. I can rank them all and return an answer in 200 milliseconds. Or I can filter, for example, all those who are more than 1 year old, all those who have really low score, all those who are really, really not in my interest pool, and only then do the ranking. This will allow me to get into much better results much faster. I might miss things, but still it will work eventually. The third thing is a little bit technical things, is what type of scripting language you use. ElasticSearch allows you to use JavaScript, Groovy, their own internal scripting language, and they even allow you to deploy Java modules to ElasticSearch. The scripting language that you will choose will influence the performance. I would recommend starting with some external scripting language, something that you can control externally. And when you found that performance considerations become more important, you can start about thinking about deploying your own Java models to do the ranking quicker and more performant. So what are the key takeaways from this talk? So what I want you to remember that search engines are great tools to implement recommendations at scale. It's easy to start, it's easy to scale, it's easy to extend, but still, it's not magic. You will still need to find your tags, you will need to decide what your user interests are, decide weights, and so on, and how to tune it. And when you think about recommendation, you need to think what makes a recommendation a good one. And it's not only CTR, it might be timeliness, it might be relevancy. You might see that diversity might bring better result than just showing the best or most relevant content for the users. So, questions? So thank you very much.